So I've got some slides coming up about where sedimentary rocks fit in the rock cycle, but before we get to that, where do sedimentary rocks fit in the rock cycle? Where do sedimentary rocks come from? Where do they go to? Okay. So we'll talk about that process of compaction, but I mean, when we're talking about igneous rocks, where do we get igneous rocks from?
Below the surface.
Below the surface, and through what kind of process?
Melting.
Okay, you've got a melt. That melt crystallizes, we get igneous rocks. Sedimentary rocks come from other rocks, not from melt, right? And so, as we'll see in a minute, we're going to be talking about process of weathering is going to be very important for providing the source of sediments. They're going to produce the sedimentary rocks, so that's why we'll talk about it first. And then you've got to have some processes that take those sediments and form them back into rocks. So, as I mentioned before, I really like this diagram, and so we'll come back to it time and time again. So basically all of this over here deals with the aspects of the sedimentary rock aspects of the rock cycle. So we're going to first talk about different processes that weather existing rocks down into different kinds of particles that make up the sediment, and then kind of in between that process of weathering on the one hand, and then lithification, which is the process for putting the rocks back together. There are a whole variety of processes that influence transport of sediments through the environment. And that's important because, oftentimes what's involved are some various transport processes that take those sediments that are being produced and concentrate them in a given area under certain conditions that will lead to the compaction and cementation, the lithification processes. Okay. So I think we've looked at this diagram before as well. We have any kind of rock, igneous, metamorphic, other sedimentary rocks can weather, which is just this process of breaking down the pre-existing rock to produce various kinds of sediments. And then we clearly have different kinds of weathering to go through. And then once those sediments are produced and moved around the environment, then we have to talk about what are the processes that essentially glue the rocks back together. Okay. So why are sedimentary rocks interesting? Let me throw that out. I should have thrown it out before throwing this up on the screen. Why are sedimentary rocks in particular so important for understanding Earth history? Brent?
Because they can contain fossils and good indicators of magnetic polar change.
Fossils. Paleomagnetism studies are mostly done in igneous rocks because igneous rocks are going to be unmagnetized as a melt, and then they're going to solidify in place in a particular orientation, and they're going to pick up the magnetic imprint during that process. And then how they move through the environment can be indicated by what we're looking at for their magnetic imprint today. So that's more important for igneous rocks, but fossils, igneous rocks are important. What important role do igneous rocks play in reconstructing the past history? Why are igneous rocks the best timekeepers in terms of absolute time?
You can tell by the grain size how long it is to float.
Not the grain size. What's our best timekeeper for absolute time? What's our clock? Yes, but those by themselves don't give us an absolute time.
Carbon
Carbon or
is,
lead or potassium argon, those radiometric dating techniques are what give us the absolute times. Okay? So when a rock crystallizes, it's going to have a certain amount of potassium-40, radioactive potassium-40, and then that's going to give off argon, and the argon's going to build up in the rock crystal over time. The potassium-40 is going to go away, and we can date when that rock crystallized. We could do that on sedimentary rocks, but we're not going to get a date on when the rocks were laid down. We're going to get a date on when the original particles that eventually made up that sedimentary rock layer were produced. Same thing with metamorphic rocks, as we'll talk about. When the metamorphic rocks undergo metamorphism, that can oftentimes screw up the radiometric clock that's in the rocks. So igneous rocks are more important for the absolute dates, but as people mentioned, the sedimentary rock layers are important for recording the sequence of life through the fossils that are in there. Why don't we see fossils in igneous rock? Because they get burned up. Okay, same thing with metamorphic rocks. You can sometimes see distorted fossils in metamorphic rocks from sedimentary rocks that have undergone metamorphism. The sedimentary rock layers are the most important for actually recording the history of life on Earth. And if we couple that with absolute age dates from intervening igneous rock, then we can we can say when did this type of biological community live and how did it change later. So going back to those Mesozoic rock layers in the Central Valley of Connecticut we looked at, we have what two types of, we had igneous rock layers like the Holyoke basalt that we looked at. We talked about sedimentary layers above and below that, right? So this layer cake of sedimentary layers, volcanic outflow, sedimentary layers, volcanic outflow that we're talking about right now, it's essentially what we had in the Central Valley of Connecticut. So we'd be able to date when the Holyoke basalt came out through radioactive dating. The sedimentary layers that are below that are older or younger? Older. The sedimentary layers that were on top of the Holyoke basalt, off to the east, would be younger. Okay? We have a variety of important resources from sedimentary rock. Lime is very important in construction, and of course, fossil fuels are the basis for our economy right now. And then, I've got my interest in Mars, and we're exploring more and more interesting sedimentary layers on Mars. So here's just a cross-section of Mount Sharp, or the stratigraphy of Mount Sharp, looking at the different layers that researchers are very interested in, because we expect it to be able to show us how climate and environmental conditions changed over the course of early Mars history. Okay, so just quickly, over the next couple of sessions, we want to talk about how weathering produces sediments and how those sediments get put back together into rocks, and how we can use sedimentary rocks to really reconstruct what conditions were like in a given area earlier in Earth's history. Basically, producing sediment from rock is essentially taking large rocky material and breaking it up into smaller bits and pieces. We'll talk about that a little bit more sophisticated way, but I mean you can see, this is clearly a big rock formation. Over time, it's going to be weathered, and it's going to produce smaller and smaller fragments. And the kind of fragments that are going to be produced are going to depend on the parent rock to begin with. So here we have, this looks like a diorite of some kind, an intermediate, intrusive rock. And obviously, as it weathers, we have to figure out what's happening to the fragments. How does that fragmentation influence the distribution of the actual minerals that made up the parent rock, and what's their fate over time? Okay. So, two basic categories of weathering: physical processes, which we're also going to include biological in terms of tree roots and so forth. Just a mechanical breakdown of the rock pieces into smaller and smaller fragments. At the same time, or in parallel, minerals in the rocks can be weathered chemically by exposure to environmental conditions. The minerals in the rock can undergo different kinds of chemical reactions and change their structure and composition. Weathering is not erosion. Weathering allows materials to be eroded away. Erosion of materials away exposes new rock surfaces to be weathered. So these processes occur in tandem, but they are different. And the erosion will tie into some of those transport processes that influence how the sediments that are being produced by weathering get moved around the environment, where they end up, and are they collecting in an area that can then lead to processes that will lithify those sediments back into sedimentary rock. Okay. Wind and water erosion. We'll talk in more detail in the last third of the course about these processes in more detail. Mass movements like landslides and creep and other kinds of processes can really move a lot of materials around the landscape. Okay. Mostly just some pretty pictures here for a couple of slides. Weathering is not necessarily this uniform process, so we get weathering and the subsequent erosion producing things like this arch formation. And so what's going on here? Why? How has weathering and erosion resulted in this kind of structure? What was this area like before the erosion and weathering and erosion was started? What would your initial condition be to result in an arch like this?
Probably a wet environment. With some water.
Well, do you build an arch by adding materials to build up the arch, or by taking materials away? Take materials away. Okay, this is like a sculpting process. It's not a clay modeling process. Okay, so originally there would have been, solid layers of stuff here, and the erosion would have, the weathering and erosion would have removed materials. The reason why you didn't get just a uniform removal of material across this matrix is that we have this capstone at the top here. How do you suppose the properties of this capstone layer compare to the layers that were underneath?
It's more resistant.
More resistant. Harder, tougher rock layer, so that, as the capstone layer, as bits and pieces of it got fractured off, carried away, and so forth, that would have exposed the underlying softer layers of sedimentary rock, to weathering and erosion, and they would be quickly removed away. And so what's limiting the process of removing material is how much of this capstone layer is being removed out of the area. And so we're now left at a fairly late stage in the process of removing all of these layers. We have one little remaining bit of the capstone layer that is to some extent protecting the softer sediments that are underneath here. At some point there must have been some kind of fracturing that's going on in these lower layers that would have exposed the interior part of this to elevated levels of weathering and erosion. And it's probably, given the environment that this is in, mostly wind erosion, and not necessarily some water erosion, but a lot of wind erosion to remove these materials. Same thing here. We have a tougher rock layer on the top, more erodible layer underneath, and so we have this capstone that's perched up here on top of this. The eventual fate of this system is what? What's eventually going to happen? It's going to fall at some point. I mean, erosion will continue to eat away from this. Erosion will continue to make this smaller and smaller, but this is probably going to erode away faster. At some point, the whole thing's going to fall over, but hopefully, well, presumably not for tens, hundreds of thousands of years, unless some yahoos come along and say, oh, wouldn't it be cool to push that over? It has happened several times in the last few years in different national parks and other protected lands. So, I mean, here's just more, how this differential weathering can lead to pretty striking landscapes. This is Monument Valley. You've got all these mesas being produced because of, again, the harder material at the top. So, people recognize this shot? That's where we were? Yeah, okay. So we would have been maybe further down the road, the crest here, but we were walking along the top. But basically the Holyoke basalt of Mount Higbee would have been exposed here on the western side due to the tilting that we talked about as the layers settled in the Central Valley with the rifting. And so where is weathering and erosion going to be taking place here? mean, you're going to get weathering and erosion on this exposed face, as well as we saw walking up along the top, we've got exposed bedrock along the top there as well. That's going to weaken the rock in processes we'll talk about in just a minute. And bits and pieces are eventually going to be weakened enough that they're going to fall off this cliff face. And so the whole cliff face over time is going to be moving from west to east, right? And so weathering and erosion is basically just eating back on those layers and from west to east like that. Okay, so here's just an overview of the different kinds of physical weathering. Basically anything that takes big pieces of rock and breaks it up into little pieces of rock through physical processes falls under these different categories. People recognize this shot?
That's right before we went to the top.
Right. So this was that little saddle, although there's a more pronounced saddle further along the trail. And we talked a little bit about this when we were in the field on Tuesday, that this was a small faulted area. You know, basically the basalt cracked, broke under the stresses as the sediments were, as the layers were settling and tilting, and that faulting opens up the interior of the rock surface to weathering, and then that triggers erosion. And so over time, you get erosion down in this area of the fault, and then also back up on either slope as weathering and water erosion work on this area. Let me skip over this, but we were talking about this dike that's going through in terms of this camptonite. Okay. Tectonic fracturing, it's a large landscape kind of process. It's not going to do a lot other. It's not by itself going to make little bitty pieces of sediment. It's going to take big pieces, break them, expose surfaces. But it's these other things that are going to be more responsible for producing the finer sediments that we're going to be talking about. And first is exfoliation. Did I miss a slide? This is a process where material is cracking off of these rock formations and following fracture stress planes that are kind of parallel to the surface of the rock. What's typically happening here, especially with a lot of these intrusive igneous rock formations like granite, remember they are formed under the surface of the earth under high amounts of pressure, and the rock crystallizes and solidifies under that high pressure environment. If weathering and erosion removes the layers of earth that are on top of that igneous rock, that granite, what happens to the pressure? The rock gets released from the pressure, basically. You don't have these tons and tons of rock laying on the surface anymore, holding the rock down. And so in response to that, the crystallization that took place when the rock was underneath the ground under all that pressure basically crystallized in response to that pressure environment in some kind of equilibrium. When you remove the overlying pressure, basically you get stresses that are pushing out from the interior of the rock, and that's going to flake off these surfaces from the different kinds of rock. Here's just another view of it from the side. So this is a fairly common kind of feature you'll see out in the field when you have these kinds of intrusive igneous forming, eroding. Half Dome in Yosemite is a good example of this. This I guess it qualifies as a batholith. This huge mass of granite, formed underground, eventually through uplift and erosion, got exposed, and so you see a whole lot of this exfoliation kind of process. Something that you'd want to be concerned about if you're doing rock climbing, right? So once there are cracks and fractures and so forth, that opens up new areas to be exposed to further physical weathering. So this is just another reference back to our trip on Tuesday. We saw these kinds of joints that had formed in the basalt. In the case we're looking at here, these joints eventually got filled in with other rock material, but in other areas you're going to see this kind of columnar jointing, and those joints are going to expose more of the rock interior to conditions that are going to lead to weathering. Okay, same thing on the top. And we talked about how that process of just physical fracturing was leading to these pieces of basalt that were laying around with these fairly angular edges that we looked at. Frost action is different than exfoliation. So how does freezing of water break rocks apart? Okay, water expands when it freezes. So with liquid water accumulating in these cracks, the water is, the liquid water is fairly incompressible. It's going to fill up that volume. When it freezes, that ice is going to expand, and that can produce a fair amount of pressure. I think people actually used to use it, by drilling a series of holes down in the rock, letting water accumulate in the fall, freezing, and eventually that pressure would break off, chunks of rock. We clearly don't have patience to do that anymore. We drill and blast and so forth, but pretty impressive what ice can do. Here's just a whole variety of pieces that have been broken up through this process. Somewhat related is this idea of joint block separation. It's again a kind of a freeze-thaw kind of thing, but depending on the crystal structure of the rock, you might see this breaking up in fairly regular, like rows and columns of material. And the more this process is taking place, the more the rock is going to be exposed to further infiltration of water, and then subsequent round of freezing is just going to continue to push this process further and further. Just some Mount Rushmore slides. Again, this is a batholith. It's not just one solid chunk of rock that you could carve. And so if you look up close, you're going to see all sorts of fracture joints, here you've got, looks like a little dike of intruded material. All of these are going to be places where the rock might be more susceptible to water infiltration. We get fairly substantial winters in South Dakota, and so freeze thawing is going to happen well, it's going to happen. So if we want to keep this around as a national monument, we have to be concerned about how exposed the carved rock is to freeze thawing. So part of what is done is to try to stabilize some of these fracture areas. If you can, fill them up with material that will keep the water from getting in, then you can slow down anyway the freeze thaw weathering of the monument. It's a losing battle, of course, but we can slow it down a bit. I think I mentioned the Crazy Horse Monument that's being constructed nearby, although at a fairly slow rate. This actually turns out to be a much less suitable rock for carving a huge monument statue like this, because it's much more riddled with cracks, and so freeze thawing is going to be an even bigger problem for this monument. Just a quick biological weathering slide. We're primarily talking about the action of plants and their roots, growing in. You can get a seed started in a small amount of organic material that's accumulated in a crevice. That's enough to get the plant going, and then as it grows, obviously, it's going to be able to exert a whole lot of pressure as its roots expand into the rock. That's just lost. Okay. So this physical processing, physical weathering is going to lead to production of a variety of sizes of smaller stuff. Typically, you're going to fall down the hillside and produce these talus slopes. So all of this stuff down here would be just debris that has fallen off the side of the mountain in response to this physical weather. In some environments, salts are a problem. So many salts, as they crystallize, also expand. And so they can do the same thing that the ice does during the freezing thawing. So there's salt encrusted around bricks. As those salts expand, they're going to put pressure on the bricks, tend to break them down. This is more a problem for the built environment, obviously, but it also happens in natural environments. It can be a big problem for ornamental structures. The more natural situation, it's more of an issue in some of the semi-arid and arid areas where you're going to get evaporation of water, pulling salts up out of the ground from the water table. The water evaporates away, the salts remain. Many of the areas where you have cliff dwellings in the southwest are situations where you have this kind of salt and freeze thaw kind of physical weathering working at these rock layers, causing the physical weathering, which then the material gets eroded away, provides a place for the indigenous peoples to develop cliff dwellings. Okay. So chemical weathering acts in concert with the physical weathering. Some materials, some minerals are just water soluble. And so when the rock containing those minerals is brought to the surface, exposed to surface conditions, and the water can get in, it's going to dissolve those minerals away. And dissolving the minerals away basically leaves gaps in the rock matrix that weakens the rock and makes it more susceptible to freeze thawing. So again, these chemical and physical weathering processes can reinforce each other. And this is probably the simplest way of where you've got some minerals that just dissolve in plain water. Sodium chloride in particular is an example. So if you've got some rock that has salt crystals in it, it's not going to hold up well to exposure to water. More important probably is the various kinds of hydrolysis processes where water reacts chemically with the minerals in the rock matrix. So potassium feldspar will weather into a form of clay, and the clay minerals that result from this chemical weathering are going to be a lot weaker than the feldspar was. And so this process is going to weaken the rock and make it more susceptible to just all kinds of weathering and erosion. We know some minerals like calcite react with acid, and so probably one of the main natural acids we have to worry about is carbonic acid, where you've got carbon dioxide mixing with water producing this weak acid. So the carbon dioxide can come from the atmosphere. So in many cases, rainfall in an area is kind of naturally slightly acidic. As that rainwater percolates through the organic material that's in the litter and soil layers above the bedrock, it's going to encounter much higher levels of carbon dioxide from the decomposition of that organic material, forming more carbonic acid. And that will eventually percolate down through the soil column, as we'll talk about later, either Tuesday or later in the course. And then that acidic material can leach materials out of the soil, but it also can break down certain kinds of bedrock, especially things that have calcite or related minerals. Of course, human activities can augment that. We don't hear as much about acid deposition as we did in the past because we've cleaned up our act a bit. But power plants, producing sulfur dioxide, nitrous oxides, to some extent, transportation systems, all are producing materials that can lead to acidic deposition, either acid rain, acid snow, or just direct acid deposition of dry material, which more of a problem out here than out west. Why is that? Okay, so we have prevailing winds coming in this direction is part of it. Corey, what did you say?
I was going to say because it rains more.
We have generally more precipitation here, but where do we have most of the power being generated? A lot more in the eastern side, in the Midwest, than out here, because why is there less power generation out here?
There's less out there, because there's less population.
Yeah. Less people, fewer power plants, less of an issue. By the time you get into the Midwest and here, you're picking up a lot more coal-fired power plants, and the prevailing westerly winds going to blow that material out here, and so it's much more of an issue out in our neck of the also does a number on the built environment as well as the natural environment. Here, just a quick overview of the places that are more susceptible to acid deposition. You have to have the acid in the atmosphere and soils that are susceptible to them to really have the biggest problems. And part of the soils that are most susceptible to acid deposition would be limestone soils because of all of the calcium carbonate. And in those areas, you can oftentimes get these karst formations that we'll look at in just a minute. Okay. So you have to have highly fractured soluble rock like limestone and have it exposed to this acidic and you get things like sinkholes and karst valleys and disappearing streams. Essentially, the rock layers underground can eventually be honeycombed through this chemical weathering process, where the limestone just gets broken down by the acidic infiltration. On the one hand, you get cool things like caverns. And we won't get any caverns, but we might get to some smaller caves during the class this semester. If the bulk of the limestone gets eroded away, you might be left with these limestone mountains that are jutting up out that just haven't been eroded yet by the acidic deposition.
Where is that?
That was probably in China. You get a lot of these karst mountain formations in different areas of China.
Fun fact about those mountains, ever since James Cameron said that parts of Avatar were inspired by those mountains, the Chinese government changed the whole thing of that range
Oh, okay.
for the movie.
Cool. In terms of environmental hazards, because we talked not only about environmental resources but also environmental hazards. Probably not as dangerous as the pyroclastic flows we were talking about with the volcanoes, but sinkholes can be a big problem. Certainly for infrastructure, for property. Every now and then there are fatalities because the ground just opens up and swallows a house. A lot of this, you have some issues with this in Florida, I know, and it would be an issue in other areas where you've got the potential to develop this kind of karst topography. So yeah, Florida, various other regions. There's some issues. I mean, I was in Indiana a couple of campuses back. And southern Indiana is a big limestone region, so there's a lot of karst formations and caves and caverns and so forth in southern Indiana as well. Oh, it says southern Indiana connected right there. Finally, oxidation. Some minerals react with oxygen and essentially rust the rock. And oftentimes you can tell because of the production of the rusty-looking products, that reaction specifically of metallic components with the oxygen again is going to break down the crystal structure, weaken the rock. oftentimes producing things like limonite. So the pyrite is the unoxidized form, and so if you've got a rock matrix that has pyrite in it, and that gets exposed to oxygen, that pyrite can be transformed into limonite, which is going to have different properties, and that's going to lead to disruptions of the crystal matrix and a weakening of the rock. Okay. Most of the iron, though, as we've talked about before, is down in the core, and oxygen's up at the top, and so this is not generally as big of an issue as some of the other hydrolysis and acid weathering of minerals into clays and so forth, but it can be an issue. And as I mentioned, this shows this is an example of the sedimentary rocks in these areas being essentially colored by the hematite and limonite and related iron oxide compounds that are rusting those sedimentary layers, providing that kind of coloration. Should have thrown up here another view of the wave, which I brought up before, but it's the same kind of thing. Those sedimentary rock layers colored orange through the oxidation of the materials. Okay. So, take-home message. We've got these two processes: physical weathering, chemical weathering, and they reinforce each other. They're going to, the physical weathering is going to expose more and more rock surface to the elements and allow chemical weathering to attack further and further into the interior of the rocks. I guess just to reinforce, we get some mineral weathering products. Clays in particular are going to be really important for the processes that produce soils, and as well different minerals as they chemically weather are going to provide a whole variety of different kinds of ions in solution. And those in particular are going to be important when we're talking about chemical sedimentary rocks that reform from the precipitation of some of these different ions. Questions?